Okay, this video takes a look at kinetic energy distribution graphs and how we can use them and how to interpret them. Speed distribution or kinetic energy distribution graphs are put in textbooks, sometimes without adequate explanation, so hopefully you can get some clarification from this video. This video also aims to increase your skills at understanding and interpreting information contained in a graph and the use of that information. And a good place to get started with kinetic energy graphs would be to look at the movement of gas particles. So here's a simulation of gas particles, and as you can see, not all of them have the same speed, so they don't have the same kinetic energy. There's a range of kinetic energies. So picture particles in a liquid. How would the kinetic energy be distributed? So here's a liquid. It's full of particles. We'll just say it's water, and each circle represents H2O. But now I'm going to do something, change the colors. So why would I do that? What do the different colors represent? Well, let's look at a x-axis where the right is high kinetic energy and the left is low kinetic energy, and we'll just pour the molecules right onto the x-axis. So what is that telling us? We've got this range of kinetic energies, and most of them are intermediate, but there's a fair amount of low kinetic energy or cold and a fair amount of high kinetic energy or hot, but most of them are more toward the middle. The thing is, you could get a graph out of this, and we see these sorts of graphs, which is the distribution of kinetic energy, and this is what it looks like. We have this line, and the higher it is, we see the y-axis number of particles, the higher it is, the more particles have that amount of kinetic energy. So what can we do with something like this? Well, if you take the average kinetic energy, what does that represent? You're right, the temperature of the liquid. But what do you think would happen to a liquid's temperature during evaporation? Now keep in mind that water has a very high attraction to itself. It has a very strong dipole, so these dipole-dipole interactions keep the water molecules together, yet evaporation does occur. So which particles are going to have enough energy to break away from its attraction to the other water particles, break away and go into the gas phase? Would it be the low temperature, low kinetic energy, or high kinetic energy, or intermediate kinetic energy particles? Let's see. So here's the temperature of our liquid right here. And if evaporation is occurring, it's the high kinetic energy particles that have enough energy to break away from the liquid. What's that going to do to the average kinetic energy? Well, it's going to decrease, and so we get a lower temperature as the high kinetic energy particles leave. Okay, and of course, the thermometer does not lie. We have a lower temperature. But we have a question to answer. Would the curve actually remain truncated at the high end that is seen here, keeping in mind that when particles crash into each other or collide, they're going to transfer their kinetic energy. So the kinetic energy would actually redistribute and look more like this. Not like this, but more like this. And so there's our new average kinetic energy, and that's our new temperature. And this would be our new curve once particles have evaporated. Let's look at that curve versus the original curve. So here's where the water started out, and here's the original average kinetic energy. Once we let particles evaporate, then the average kinetic energy decreased and the temperature decreased. The question that this can answer, this curve that we're looking at right here, is it should be able to tell us how sweat can cool our body down, and sweat, of course, being mostly water. And what is water in the sweat doing? The sweat is just sitting on top of your skin. What's it doing? How's it cooling down your body?
So that is a great question that so wonderfully lies at the intersection of biology, physics, and chemistry. But rather than answer that, let's look at an analogy to what sweat is doing. And the analogy is what's going to happen to the temperature of a glass of water sitting on your kitchen table. And we will assume that the water starts out at room temperature. So the water is evaporating, and we saw before that evaporating water will cool down. Let's evaporate some water, and as we saw previously, the temperature of the liquid decreases, and so now it's slightly lower temperature than the air. If the water is slightly lower temperature than the air, what's going to happen? The air, being slightly warmer, will transfer heat right back into the water, and that heat transfer will cease once the water is back up to room temperature. So the water really never gets below room temperature. Any slight drop below room temperature, it will just be warmed right back up to room temperature by the air surrounding it, by the heat transfer from the air. So this keeps on happening as evaporation occurs. It keeps getting heated back up to room temperature, and eventually you have very little water left. And this would take place if you did it in your kitchen with a thermometer in it. It might take 2 or 3 days. This can tell us why sweat will cool your body. Think about it.